Hey guys, I hope all is well. This is just going to be a little homework help video. So for some assignments, I will send one of these out where I just do a couple problems that are like representative of a lot of the homework problem types you'll do during that section. Um, I didn't do this in the last section because you guys had quite a bit of stuff to do already, obviously, and a lot of videos to watch. I hope it shells out a little bit from here. I hope that you saw chapters 7 and 8 in your last statistics class. It seems like some people struggled with it a little bit more than others. If that's happening to you, just make sure to reach out to me. I'm happy to help as you're working on the homework. I don't want you to get bogged down. So if it's taking you an insane amount of time specifically, reach out to me. Um, so here's a representative homework problem. This is obviously about hypothesis testing. So it says a report states that adults 18 to 24 years old send and receive 128 texts every day. Suppose we take a sample of 25 to 34-year-olds to see if their mean number of daily texts differs from, that's going to be a key word right there, the mean for 18 and 24-year-olds. State the null and alternative hypotheses we should use to test whether the population mean daily number of texts for 25 to 34-year-olds differs from the population daily mean number of texts for 18 to 24-year-olds. Enter exclamation point equals for as needed. So if you remember from my earlier videos about hypothesis testing, I think 2.1, there's really three types of hypothesis research questions we could have: less than, greater than, or different than. And you can use a lot of different words to say those same things, but they'll always be in one of those three categories. And so this is obviously in the differs from category. I always like to start with the alternative hypothesis. The alternative hypothesis will be true if the answer to the research question is yes. So they will differ. That would mean that mu, so it gives us this little math thing to use. We have to go find mu. Mu, I'm going to get rid of my face. That was creepy. That was like an alien. Mu is not equal to, what number? 128 is the 18 to 20-year-olds. And we're asking 18 to 24-year-olds. We're asking if 25 to 34-year-olds differ from that. Mu here represents the true population mean texts per day for 25 to 34-year-olds. That's the number we don't know. What we do know is that 18 to 24-year-olds are 128. So that's what we're comparing our unknown mu to. That was a sweet rhyme. 128. So now that I know that, I can remember a couple of my other rules. Well, the null is always the opposite, basically, and the null always includes equality. So those lead me to believe that the null hypothesis in this case will be that mu equals 128. Okay? So the null hypothesis is that 18 and 24-year-olds and 25 to 34-year-olds text at the same rate. The alternative is that they text at different rates, but we're not asking whether it's greater or less, just different. Okay? Suppose a sample of 30. I'm going to go ahead and open Excel and start doing stuff. Oh, this is my practice version, but let's delete it and pretend I didn't practice. I'm going to start going through and filling out the stats that I need. So that's the first one they've given me, a sample of 30. So that means n is going to be 30, right? 25 to 34-year-olds showed a sample mean, that right about there, x bar, 118.1 texts per day. Assume my population, standard deviation of 33.17. I'm going to go ahead and put PSD right here because that will remind me that I'm dealing with a population standard deviation. Why does that matter? Oh, you know. You know why it matters. So we're going to go ahead and compute a p-value based on this data so far. So the question is, let's talk a little bit about statistics, you guys. The question is, why do I have to keep going if I've found that the average for 25 to 34-year-olds is 118.1? I know that the average for 18 to 24-year-olds is 128. I know that 118 is less than 128, so can't I just stop and be like, yes, they're different? The answer is no. No, because this 118.1 is just the sample average from this sample of 30. And you know that sample averages, X bars, are a random variable. If we took a different random sample of 30 people and calculated the sample mean, it's very unlikely that we would get exactly the same number, especially given this standard deviation, right? In fact, maybe we get 130 in that sample. Now I have two different samples showing the opposite conclusions. Well, that's what we have to get at. We have to get at how much information is this one sample really giving me? And to get there, we have to either do p-values for the p-value approach, or down here we're going to do the critical value approach in a second. Generally, I would always guide you towards the p-value approach. And by the end of the semester, because we're going to continue to do hypothesis testing throughout the semester, the class will converge basically to the p-value approach. So in order to calculate the p-value, that is the answer to the following question. What is the probability that I landed at 118.1 or farther away if this number came from a distribution centered at 128? As you guys know, if the truth is 128, then we have a bell curve that is centered at 128. And if I take a random sample, I'm going to probably get numbers that are not exactly 128. But what we need to think about, what's the probability of getting this particular number? If getting a number this far away from 128 has a very big probability in the distribution, then we'll be like, no, I don't have any evidence that they're different, because there's a high probability that I would see what I did see or observe what I observed in a world where the null hypothesis is true or they are the same. Texts are the same. On the other hand, if we find that the probability of landing this far away from 128 is extremely low in a distribution centered at 128, then we'll say, this actually does provide evidence that 25 to 34-year-olds text at different rates than 18 to 24-year-olds. So that is what the p-value is going to allow us to do. And that's why we have to keep going and cannot just stop once we observe the X bar. So we're going to need a standard error, because that tells us this standard deviation tells us about how texting deviates from individual to individual in the sample. The standard error tells us how much X bar moves around when we take different samples. And we know the formula for that is the population standard deviation, or really any standard deviation, divided by the square root of the sample size. So now, thinking about these probabilities, going back to previous lessons in this class from the last section, one thing that we learned to calculate the probabilities using were z-statistics. And I can convert any X bar and null hypothesis combination to a z-statistic if I know the standard error. So the z-statistic in this case, from the formula, is equal to X bar minus 128, which is often referred to as mu naught. We call that little zero right there. We say H naught for the null hypothesis. We might call it mu naught is the null mean. which is 128 in this case, divided by the standard error, and that's how we get a z statistic, right? So now we have to decide, I'm just checking that I typed everything in right, 118.1, 33.17, 30, they wrote right there. The standard error is the population standard deviation divided by the square root of 30. Checking those things throughout, because if I land way down here and then everything's red, then I probably have to basically start over. So I like to check a lot throughout the problems. I don't know if that's good advice or just something that I do, but it definitely helps me. So now what are we going to say? Well, the probability of landing this far away from 0 in a z distribution is the same as the probability of landing this far away from 128 in that distribution. We just converted the centered at 128 distribution, this number coming from that distribution, to an equivalent value in terms of standard errors, which we call z statistics or t statistics. So now we have a standard, the number of standard errors we landed away is what that number really can be thought of. This is 1.63 standard errors below 128. And now we can ask, well, what's the probability in that tail? That's equal to norm dot dist. I'm going to write, I didn't label it, sorry. I'm going to write P being less than z, because we have to think about the fact that this number is negative, by the way, right? So we want the area outside the z statistic. Because I have a negative number, I want the area to the left of it. Note that if you had a positive test statistic, you would want to look to the area to the right of it. So in this case, I'll do equals norm dot dist. This guy, comma 0, comma 1, comma true. 0 is because the z distribution is centered at 0, has a mean of 0. The z distribution has a standard deviation of 1. True, just always put true there. Don't worry about it. 5.1% is the probability in that tail of the z distribution. Similarly, 5.1% is the probability of landing here or to the left of that from a normal distribution centered at 128 that has this standard error. Whoa, play that in slow motion. Now, one thing we have to be really careful about right now is that this, if we did a one-tail test and our research question was, is it less than? This would be our p-value right here. That would be the answer. However, we are doing a two-tailed test, and when we're doing a two-tailed test, we have to consider the probability of landing in the upper tail as well, because we didn't give any direction to our research question, and I account for that by going ahead and taking my p-value and multiplying it by 2. You just double it. The reason that works is because a z distribution is symmetric. So the area to the left of negative 1.63 is the same as the area to the right of positive 1.63. So in a two-tailed test with the equals and not equals, we have to remember to double the p-value. But you do not do that in a one-tailed test. Okay, they want 4 decimal places. Our alpha is 0.05. Now, what does alpha tell us? Alpha 0.05, or 5%, means we will only reject the null hypothesis if our probability of being wrong by doing so is less than 5%. Another interpretation of the p-value, this 0.1021 or 10.21%, is to say, if I reject the null hypothesis and say, yeah, they are different, they do text at different rates, there will be a 10.21% chance that I am wrong. Now, this says alpha is 5%. My probability of being wrong is greater than 5%, so I do not reject the null hypothesis. Now, this is tricky because they say do not reject HO. We can conclude that the population mean daily text differs significantly from. No, that is not what the null hypothesis says. It says that they're equal or do not differ. Do not reject. We cannot conclude that the population mean daily text differs significantly from. So you have to be careful about those, right? Not only do we have to say whether we reject or not, we have to remember what the null hypothesis means. So that's important. Repeat the preceding hypothesis test using the critical value approach. State the null and alternative hypotheses. The null and alternative hypotheses do not change based on whether we are doing the p-value approach or the critical value approach. They're the same because remember, those are based off the research question, right? In that first video, we didn't need to know which one of those approaches we were doing to set those hypotheses up. Find the value of the test statistic. We already found it. It's the z-score. We found the test statistic on the way to getting our p-value. So it's right there. 2 decimal places makes that minus 1.63. State the critical value. So now we have to do something new. We compare our p-value to our alpha. We compare our our test statistic to a critical value. All we do for this is we basically convert our alpha of 0.05 to the corresponding z-value. So in this case, we have to remember to have 5% total in the tails. How much do I need in each tail? 0.25%. So this is going to be equal to norm. Try to think of what this number is going to be before we find it, because you've seen it a lot of times at this point. Or we're going to do inverse, right? Because we're going to put in a probability 0.025. That's the area to the left of this number, comma, from a z distribution, mean of 0, standard deviation of 1. No surprises there, negative 1.96. You've seen that number a lot before, right? Positive 2. Because that's what we use for a 95% confidence interval if we know the population standard deviation or if we're doing a proportion problem. So there's no surprises there. State the value, though. They want 2 decimal places. So they want exactly that 1.96. I have to be careful here because if it's less than the negative 1, I'll reject. Or if it's greater than the positive 1, I'll reject. So comparing, let's do the comparison real first. We landed 1.63 standard errors to the left of the null hypothesis. In order to reject the null hypothesis, we needed to land 1.96 standard errors to the left of the null hypothesis. Also, we could imagine a situation where we get a positive or a sample mean that's greater than 128 and a positive test statistic. If that had happened, our test statistic would have needed to be greater than or equal to 1.96. So when you're doing a 2-tail test, you have to think about both tails. This is the tail we actually ended up looking at, but we could have ended up looking at this tail. That's a possibility. We just found out that we didn't after we observed the 118.1 sample mean, which is lower than 128. Okay, state our conclusion. It's the same as the conclusion above. You should always get the same conclusion from the p-value approach and the critical value approach. If for some reason you get a different conclusion, something has gone wrong in the math in the problem. So now we cross our fingers and pray Boop-a-doop-a-doop boop. Oh no. Okay, that was question 1. We didn't do that. Stop judging, you guys. Oh, green. Oh, hello. Hello. Ding, 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 ding. Okay, cool. See, if you're careful, it can happen. It can happen. Should we try another one? Or is this taking too long? Let's do a bonus one. And you guys can just stop the video right here if you're sick of this, because I'm sure it's getting pretty bad on your end. Let's try homework 9.4. Preview assignment. I want to do this one because it has data. Data. Maybe I should keep this stuff because it is helpful. You may need to use the appropriate technology. We don't care. Jones Nursery specializes in custom designed landscaping for residential areas. The estimated labor costs associated with a particular landscaping proposal is based on the number of plantings of trees, shrubs, and so on to be used for the project. For cost estimating purposes, managers use 2 hours of labor time for the planting of a medium-sized tree. Actual times from a sample of 10 plantings during the past month follow times in hours. Ooh. Command C or Control C. We can do paste special. I think we want text because this one's weird, and then I'll just paste it right. You could turn this into a column, but we can do all this stuff in rows. With a 0.05 level of significance, alpha equals 0.05 is what that says. Test to see whether the mean tree planting time differs from 2 hours. State the null and alternative hypothesis. Differs from. Ooh, we're doing another two-tail. I think that one, right? Null equals, alternative does not equal, 2 hours. Yeah, those are the only ones I even see with equals and not equals, right? Compute the sample mean. Equals average. Click on the first one. Shift, Command, or Control over. Enter. 2.2. Uh-oh, we're overworking these guys or underpaying them. Something's going on. Compute the sample standard deviation. SSD equals SCDEV.S. Click on it, shift it, command it, right, enter it. N equals count. Ooh, thank you for counting, Excel. 10, SE, we know what the SE is. So small sample size. We need to plant more trees. ZStat equals something or the other. X bar probably. Minus mu naught maybe. Divided by the standard error. The probability of being less than that? No, I'm going to go with the probability of being greater than that, right? Because that's above my null hypothesis. That's going to be equal to, there's a couple ways to do this. Norm t dot dist y, pause and answer y, or just answer y without pausing. X, so maybe I should actually change this to t too, right? And then change this to t. Why am I doing this? You know the answer now. S, sample standard deviation. That's when we use t statistics. This is above, this is a positive test statistic, so I'm going to ask what's the probability of landing in that tail above. So the probability of being greater than that is going to be t dot dist This is the number. We have to be very careful here, though, because this is going to give us the probability to the left. I want the probability to the right of that number. Degrees of freedom is n minus 1, comma, true always. So how can we get to the number to the right of this number? One way we can do it is by doing 1 minus the probability of that. That's the probability to the left, right? So the probability to the right of that is 1 minus that, because they have to add to 1, because the area of the whole bell curve is 1. Another way to do it is say, like, oh, it's a symmetric distribution. So the probability of being to the left of the negative version of this number is the same as the probability of being to the right of the upper one. But you just have to be careful and think about that when you're calculating those probabilities if you're looking to the right, which we are in this case. Now we're doing a two-tailed test again, right? So that means that we take this and multiply it by 2 to consider the possibility that we landed in the lower tail. In this case, we landed in the upper tail, but it's always possible we would have landed in the lower. I don't even know if I had to do all that stuff, dude. SSD wants us to calculate that. I'm going to check the sample. 1.6, 1.4, 2.7, 2.3, 2.5, 2.3, 2.6, 3, 1.3, 2.3. That looks right. Okay. Compute the sample standard deviation, 0.575. What is the test statistic? The test statistic is this t-stat right here. Note that this t-stat and the z-stat calculation is basically exactly the same. It's just whether you're using sample or population. What is it? 3 decimals is 1.099. What is the p-value? I did need to do it. 4.0.3002 is about 4. What is your conclusion? We are not rejecting that. That is a huge p-value. Do not reject, we cannot conclude. They flipped it. Is anybody else scared? That one seemed like easy. Do the first one again. Oh, it's green, it's green, it's green, it's green, it's green. See you guys later. Quit while you're ahead.